Okay, in U4A1, we took a quick look at orbits, forces and fields, and we did two calculations. We looked at how far away a satellite would be above the Earth, and we looked at its velocity. Now, for U4A2 through A5, we're going to be looking at electrical forces and electrical fields. A couple little background points that are going to be really important as we go through here. First of all, when we're talking about electricity, we're talking about electrons. Now, the charges may come into play as we go. The charges are in coulombs. These are just things that you have to have written down or remember. Protons are plus, electrons are negative. Both of them have the exact same charge, 1.6 times 10 to the negative 19. This is really interesting because if you look at the size of a proton, it's much bigger than an electron. Now these are called relative sizes. An electron is not really zero. It's 118/37 the size of a proton. So there is quite the difference, but remarkably, their charges are the same. Now these charges are measured in things called coulombs. So that's going to be a capital C. And you won't always get these charges. They may give you other charges also. Really important to remember that opposites attract, so positives minuses, a positive charge and a negative charge will attract and like charges repel. This formula will not be used a lot in this course, but if you have a number of electrons and you want to know what the total charge is, you take the charge on one electron, 1.6 times 10 to the negative 19, and you multiply it by the number of electrons you have. And once again, that's going to be measured in coulombs. Okay, here we go. This formula is probably going to look familiar. What we're looking at is electric force. So this is the force that two charged particles exert on each other. So let's say we had an electron and a proton. What type of force would they exert on each other? Well, we have a constant. Our constant is 9 times 10 to the 9 newtons meters squared over c squared. Now, c is coulombs, by the way. All this does is marry together all of the different units that are in this formula. So newtons here, coulombs here, radius here. Radius is the distance between particles in meters, which could be tricky with what we're doing because we're going to be doing small distances. These are the charges on your particles. Remember, when we did gravity, it was mass. Now we're doing charge as we go along. There are two types of problems you have to do in U4A2. So here's what you're trying to figure out. So first of all, we're going to do one-dimensional problems. So this is the first type of problem. This is one-dimensional. You have three different charged particles, Q1, Q2, and Q3, and what we're trying to do is see how Q1 affects Q2 and how Q3 affects Q2. So this is the one we're focusing on right here. Now, first thing you do is you look at the charges. They're both positive, so the Q1 is going to be pushing the Q2 this way. Now, the Q3 is negative and the Q2 is positive, so the Q3 is going to be pulling this way. You're going to have two sets of things you're going to have to look at in these types of problems. You focus on what the particle is that we're examining, and then we focus on the other particles with that particle. So it's going to be Q1 and Q2, and it's going to be Q3 and Q2. Those are the two calculations you're going to do. So you're going to use the formula up here. You're going to find the force of Q1 on Q2, including direction. We already said it's pushing this to the right. Then you're going to find the force of Q3 on Q2 and the direction. Then you add up the net force. So you add up what you get for part 1, you add up what you get with what you get for part 2, and make sure you have a direction there, such as to the right or to the left. If this was pushing back this way, this one would be positive, this one would be negative. You have to take into account that one is going to the right, one is going to the left when you add them up. Now, here's the second type of question that you're going to have to be able to do for testing purposes. Things are not always in one dimension. So we might have a two-dimensional situation. I would highly suggest that you watch this twice. we have 3 particles. This is the one we're focusing on right here. So we want to know how this affects this and how this affects this. Excuse me for 1 second. So once again, we want to know the effect of 2 on 1 and the effect of 3 on 1. So what you will see is that 2 and 1 are on the same plane. They're going in sort of a y direction here, positive y direction. These are 30 centimeters apart, and these two are 52 centimeters apart. So by Pythagorean, if we wanted it, we could find this distance right here, which we're going to need to do our calculations. So c equals the square root of a squared plus b squared. We will need that. So let's focus on Q2 and Q1. We'll use our force calculation, and we will determine, I believe, a force of about 247.5. So what you're going to do is use these two right here. There's our 2Q values. We've got our constant. We have our radius here, and we can get that force. So that force is going to be pushing straight up because this is positive and this is positive. So they're going to repel. This is going to push this straight up with a force of 247.5. Now what you want to do is you want to take a look at this particle here. It's negative. This is positive. So this is going to be pulling this towards it. Where this is pushing away, this is going to be pulling towards it. So you want to take your 2Q values. Oh, by the way, these guys are microcoulombs. So to put these into the equation, you have to divide them by 1 million to do that, to get them in coulombs. So that's a mu or a micro. You have to divide these values by 1 million to get this to work. You've got the radius that you've calculated through Pythagorean. You've got a k value. That's a constant, 9 times 10 to the 9. You've got your 2 coulombs right here. And then what you can do is draw a scale diagram. So you make up a scale and you draw a scale for 247.5. So let's say that every Newton is 1/10 of a centimeter. So that would be 24.75 centimeters. And here you do the same thing and you draw a scale vector. And what you have to do is you have to find this angle here from this original diagram. So tan theta equals opposite over adjacent, and you get a tan of 60. Now that you know this distance, and this angle, you can get this angle right here. Because not only do you need to know the force, you need to know the angle. So let me back up for a minute. We know that Q2 is pushing Q1 outwards with a force of 247.5. We did the force calculation. Force equals KQQ over R squared. We know that Q3 is pulling Q1 towards it with a force of 96.25 because we did the same calculation. We know this angle is 60 degrees because we took the angle here and used opposite over adjacent. We can now draw in our resultant line from the beginning to the end. And if we measure that, we've got the force of the resultant. That's the force that this is exerting on this and this is exerting on this. This is the net force. If you draw a scale diagram, you can get this net force right here. You need this angle. Because we have a vector, you do need a direction, and I believe that's 16 degrees. So you may have to use the sine law to do that. Folks, you have to figure out how to do problems in 2 dimensions, how to do problems in 1 dimension, and you have to know the formula here. This is the major formula here. This one's minor.